now we're going to use what we know about heat and reactions to look at reaction rates. So a rate is the measure of the speed of change occurring within an interval of time. So if you think about your travels, you're measuring how far you go in a certain amount of time, your miles per hour. With chemistry, we're going to look at how much reactant is changing per unit of time. And we're going to relate these to the properties of the particles that we're talking about. So collision theory, particles can form products if there is enough kinetic energy when they collide. So the minimum amount of energy that particles must have in order to react is called the activation energy. So you're going to have two particles, they're kind of floating about in a solution. If there is enough energy when they run into each other, then you will get a product. If there is not enough energy, they're just going to bounce off of each other and continue about their random motion until enough energy is supplied, either through you providing heat or adding a catalyst. So the activation energy, you're going to have to look at an energy diagram here. I do need you to draw this. So some points up here at the top, this is your activated complex. So this is that transition state where you're going from reactants to products. So the energy from where your reactants energy is to the top of that is the activation energy. How much energy do you have to put in to get to that activated complex so that you can produce products? This is a very unstable structure. It only lasts about 10 to the negative 13th of a second. And like I said, it connects your reactants to your products. So this is the energy that your reactants are starting with. This is the energy that your product is finishing with. And this change is the heat of the reaction. So the higher the activation energy, the slower the reaction's going to go. Think of it as trying to ride a bike over a little bump or a giant mountain. It's going to take you less energy to get over the little bump than it is up and over a giant mountain. So same thing here. The higher the activation energy, the more energy is going to be required for that reaction to go. So we can modify a reaction rate by varying the conditions of the reaction. And the first thing we have control over changing is the temperature. If you increase the temperature, you're going to increase that kinetic energy, so they're going to move around faster, and then you're more likely to have a collision. So this is going to let you form products faster. Next is quantity. So if you have more particles in the solution, then they're more than likely to collide with each other, and that's going to increase the reaction rate. So think of temperature as you walking around the room versus running around the room. If you all got up and walked around, you're probably less likely to run into each other. If you got up and I told you to run around the room, then more than likely you're going to have a collision. And same thing here with quantity. If I told two of you to get up and run around the room, you're probably not going to run into each other. But if I told all of you to get up and run around the room, odds are someone's going to run into someone else. Next is the particle size. So if you have smaller particles, that's going to increase the surface area. So think about what we did with the Alka-Seltzer tablet. You had the defined surface area of that tablet. When we crushed it up, though, you could spread it out in a thin layer over a larger surface. So you've increased the surface area. And when you do that, you're more than likely to have more collisions, and that's going to increase the reaction rate. So some things to increase surface area: you can either dissolve the solid or crush it into a fine powder. A catalyst is the last thing. So you can add a chemical that's going to lower the activation energy of that reaction. So you're going to drop the curve. They're not consumed in a reaction, so they're not going to be included on the reactant or product side. Instead, they're going to be written over the yield sign. So here's an energy diagram. The red line is the regular reaction by itself. And then here with this dotted green line, you can see that we've added the catalyst. So you've lowered, lowered the activation energy. Therefore, less energy has to go into the reaction to make it go. Energy diagrams for endothermic. Remember, endothermic, you are putting energy into the reaction. So you're going to wind up with your products having a higher energy than your reactants. You had to put heat in to make this reaction go. And with exothermic, heat's going to be released. So your products are going to have a lower energy than your reactant.